All right, Gen Chem kids, we are going to do some colligative properties today. This is an extension of our unit on solutions, and we have discussed what different mixtures are and what it takes to make a solution. We've spent a couple of days talking about concentrations of solutions and learning how to use molarity and molality. Now, this time, we are going to learn about some of the properties that having mixtures in a solution actually give that solution. Today we're going to talk about colligative properties. Now I want to define what a colligative property means, and we're going to talk about 4 different colligative properties. Okay, so colligative properties, let's define it right here, is a property of a solution. So a property of a solution. So it has to be dissolved down to the molecule level. It has to be a solution that, we changed color. That depends on the number of particles dissolved, not the type. So it doesn't really matter what I dissolve in my solvent. What does matter is how much or the number of particles that I have dissolved in that solvent. Okay, there are 4 main colligative properties that we are going to discuss. We're going to discuss some of them in more detail than others. So the first colligative property is vapor pressure lowering. Some people also call it vapor pressure depression. Okay, so that's both of the ways that you can, the vocab for it, vapor pressure lowering or vapor pressure depression. We also have freezing point depression. And for our third one, we have boiling point elevation. And for our fourth one, we have osmotic pressure. So all 4 of these things, the vapor pressure, the freezing point, the boiling point, and the osmotic pressure can all be changed based on the number of particles that I have dissolved in a solution. Okay, let's talk about vapor pressure lowering or vapor pressure depression first. Okay, in this beaker, I have a beaker of pure water. So it's just water in here. Okay, so I have a pretty dumb question. What is on the surface? So this surface where the water meets the atmosphere, what's on the surface of that water or that liquid? Hopefully you say all water, right? That surface is water. All of it is water, okay, as that surface comes in contact with the air above it, okay? Can those water molecules, can they evaporate and create what is called a vapor pressure? Yeah, they can. All the time, we're going to have little molecules coming off of that surface if they have enough kinetic energy to break away from their neighbors. That's why when we leave a bottle of water out, or a glass of water out, or water on the table surface out for a long time, we come back and it's dry. It evaporates off. So when these molecules go into the air above it, it creates kind of a pressure. And that pressure pushes against the atmosphere. So we have the vapor pressure from the liquid pushing against the atmospheric pressure. And that pressure balance gives us a lot of different things that we can play with. Okay, So at room temperature, the pressure of these water molecules coming off that surface is not very big. It's about 24 millimeters of mercury, which is not very big at all. To give you some scale, normal atmospheric pressure at sea level is about 750 or 760 millimeters of mercury. So the vapor pressure of the water coming up off the liquid is very small compared to the atmospheric pressure pushing down on it, but it's still there. So think about when we put a pot of water on the stove to boil. What happens when those bubbles of water are coming up out of that water? Okay. When water is heating to boiling, and we're talking at sea level, which is what we call normal pressure. Okay. At sea level, water will boil at 100 degrees Celsius. The vapor pressure when that water starts to boil is the same as the atmospheric pressure. So in order for something to boil, the vapor pressure, the molecules coming off of that liquid surface, have to be equal to the atmospheric pressure for it to boil. Otherwise, the bubbles can't escape that liquid. So it has to be 760 millimeters of mercury to boil. Okay, so boiling is where the vapor pressure of the liquid is equal to the atmospheric pressure. Okay, in order for something to boil, the vapor pressure of that liquid has to be the same as the atmospheric pressure. Otherwise, it will not boil. Okay, so let's think about this beaker. If I put 10% of it as sugar, so that means I'm going to have sugar molecules all through this liquid, right? I'm just going to make little orange dots to make that sugar. So, another dumb question. Now that I have sugar molecules all through this liquid, what's on the surface of that liquid? Is it pure water anymore? No. You notice I have some orange dots there. So, what's on the surface of the liquid is sugar and water molecules. Okay, so what do you think happens to the vapor pressure of that water now that I've got sugar molecules and water molecules at the surface? Think about that for a second. Okay, do you think that some of those sugar molecules might get in the way of all the molecules of water actually evaporating? They do. So the vapor pressure goes lower. The sugar molecules get in the way of some water molecules evaporating. And because the sugar molecules get in the way of some of the water molecules evaporating, that means the vapor pressure of that solution, we've got a mixture now, will go lower. So the vapor pressure decreases. Okay, so the vapor pressure decreases, or it's depressed. Okay, so at the room temperature now with the sugar in there, and since I have 10% sugar, that new vapor pressure will be about 10% lower than what we would normally have with pure water, which Since our normal vapor pressure of water at room temperature was about 24 millimeters of mercury, if I take 10% off of 24, that gives me 2.4. So I would expect about 21.6. Oops, I wonder why that happened. I would expect about 21.6 millimeters of mercury, okay, for my water vapor pressure. So that coligative property is called vapor pressure lowering. And sometimes some people call it vapor pressure depression. Okay, because anything that is low is depressed. So we've depressed the vapor pressure. Okay, so what do you think would happen if I took this same beaker that now has sugar in it and I heated it to 100 degrees? Oh boy. I'm sorry. I don't know why this always jumps like 10 minutes into our lectures. Okay, so what would happen if I took this same solution and I heated it up to 100 degrees? Okay, so if that was heated up to 100 degrees, that vapor pressure would still be about 10% lower. Because I've got 10% sugar solution getting in the way. So I would expect that vapor pressure, and now it's jumped again. Okay. So this solution is going to be about 10% lower because that 10% sugar solution. So at normal pure water, we would expect it to be 760 millimeters of mercury to boil. But 10% lower, we would expect the pressure, the vapor pressure, to be about 684 millimeters of mercury. Okay? Now, remember, for something to boil, the vapor pressure has to equal the atmospheric pressure. Does this vapor pressure equal the atmospheric pressure of 760? No, it's not high enough. So will this solution boil at this temperature, even though we've brought it to 100 degrees? No, it will not. It won't boil because the vapor pressure does not equal the atmospheric pressure. Now remember, for something to boil, the vapor pressure of that liquid has to equal the atmospheric pressure or be bigger or greater than that. Okay? So the vapor pressure of the solution is lower than 760, so the solution will not boil. Okay? So what are we going to have to do to get that solution to boil? We have to get that vapor pressure to raise. And in order to get that vapor pressure to raise, we are going to have to heat that solution up even hotter. even more. So it's going to have to be even hotter. Okay, so this is a colligative property called vapor, or not vapor pressure, boiling point elevation. Okay, so we can lower the vapor pressure by putting a solute in our mixture and making a solution. We can raise the boiling point. It turns out it doesn't matter if the solute is sugar or something else. Remember, colligative properties, it doesn't matter what is dissolved, it just matters how much. So long as 10% of the solution is made of solute particles, both the vapor pressure lowering and the boiling point elevations will be the same. It doesn't matter what, it just needs to be 10%. Okay, so there are two other colligative properties that we're going to talk about. We're going to talk about freezing point depression and osmotic pressure. Okay, so those are the two other colligative properties that we are going to talk about today. Okay, so let's think about why the freezing point would go lower if we had a solute dissolved in to make a solution. Okay, now think about this. If I have a molecule that is not the solvent in there as the solvent is trying to freeze, what happens as we try to freeze? Let's think about that as a molecule level. I'm trying to go from the liquid state to the solid state. Now, if you remember from your 8th grade chemistry class, or not chemistry, but science class, in the solid state, the molecules are in nice little rows. They're in a crystalline form. And if I want to get those molecules nice and lined up and able to be attracted to each other, they've got to get next to each other in a nice, perfect pattern. If I have a foreign object in there, if I put like a foreign molecule in there, it ruins that nice crystal pattern. And so having that solute in there ruins that crystalline structure. It ruins that pattern and makes it harder to make that solid shape. So the solute interferes with the crystals of a solid forming and makes it harder to freeze. So in order to actually get the molecules to freeze, we have to take the temperature down even lower. Okay, so it makes our freezing point even lower than normal, freezing point depression. To freeze, the solution, let's spell that right, solution has to be even colder than the pure solvent. Okay, so let's think about this. Why then do we put salt on our roads after a snowstorm? Think about it. Is that salt going to interfere with the freezing of the snow and the ice on the roads? Yeah, it will interfere with that freezing. And because it interferes with that freezing, it makes the snow and the ice on our roads, the freezing point becomes depressed, and it keeps that snow and that ice in the liquid state instead of freezing. It's a lot easier to drive on water than it is to drive on ice. Okay, so we spend a lot of money here in Utah every winter putting salt on the road to interfere with that snow and ice freezing. It interferes with the snow and ice crystal formation, i.e. freezing, and keeps it liquid. Okay, so it lowers that freezing point. It lowers the freezing point. And keeping that snow or ice liquid makes it so much safer for us to drive. We spend a lot of money with the snow plows, the trucks, the drivers and stuff, but in the end, it actually saves us money because it saves on auto insurance, it saves on medical bills because people don't get into accidents. So it's a lot cheaper to do it this way than to have all the accidents and the medical bills and things that we would have with icy conditions and all the accidents that we would have. Okay, so that's why we put salt on our roads after a snowstorm. All right, let's go to our next property. If it will let me scroll. Okay, some more examples. The more ions, now these are soluble ions, and when ions dissolve into a solution, they affect the freezing point even more. Let me give you an example here, a couple of examples. So our first example, we used sugar. I'm going to use glucose, which is a form of sugar. When I put it in water, it stays together. So I would get, for 1 mole of glucose, I would get 1 mole of particles. Because it does not ionize, it doesn't break apart, or not ionize, but separate, okay? But sodium chloride, for example, the salt that we use on table salt, is soluble. And when we dissolve that into water, it doesn't stay together. The ions are actually more attracted to the water, so that it breaks apart. So we would actually get a sodium ion and a chloride ion. So we would actually get 2 moles of particles. So that would change our freezing point twice as much as we would normally expect, because I get 2 moles of particles instead of 1 mole of particles. So if I use a salt that can dissolve into even more ions, I would get an even greater effect. So a lot of times here in Utah, we use magnesium chloride, because magnesium chloride is really easy for us to get in the Great Salt Lake. We actually have you guys ever heard of MagCorp out by the Great Salt Lake on our way to Lake Tooele? They get a lot of salt out of the Great Salt Lake. So we would get a magnesium ion and 2 chloride ions. So we would get 1, 2, 3. You get 3 moles of particles. Okay, so the more ions that we can dissolve into that solution, we will get more particles, which means our effect will be even greater. So our temperature change here would be 3 times as much as what we would see with the sugar or the glucose. The sodium chloride would be 2 times as much. Okay? All right, let's think about this. Why do we put, if you've ever flown in the winter time, why do we put de-icing agent on the airplanes when it's winter? Why do we do that? Why would we want to de-ice the plane? Okay, let's look at a picture of a plane. This is a picture, of a plane being sprayed down with de-icing agent. Now, this is a solution. we are using the coligative property of freezing point depression. So we are using our freezing point depression, which is decreasing that freezing point. Okay? Now, if you've ever sat in the seat right by the wings, you'll see that on the wings there are flaps that need to be able to move up and down for the plane to be able to steer and to land. There are also flaps here on the ends of the tails that the pilots also control to steer and get the plane to lift or to land. Okay? We want those flaps to not freeze. We want those flaps to be movable, so that we can steer and maneuver the plane. If those flaps in the wintertime go up in the air and freeze and they can't move, that means the pilot cannot control the plane and the plane is going to end up crashing. So we use these de-icing solutions to keep the plane's flaps movable so we can control the plane and have a safe journey. Okay? Why? For those of you who are into cars, why do we put antifreeze in our cars in the cooling system? There's two reasons. It's called antifreeze, right? Which means that we are going to not freeze, right? Anti, against freezing. So it keeps the water that we use in the cooling system from freezing, okay? Keeps the water in the cooling system from freezing. Now, there's two reasons why we don't want the water in that cooling system to freeze. One, we want the water to be able to circulate and keep that engine cool, okay? And two, if you've ever seen water freeze, you know it expands. If that water freezes while it's still in the engine block and it expands, it would crack the engine block and you would have to get a new engine block. That's several $1,000s, by the way. The other thing is when it is hot, we also use antifreeze because it lowers that boiling, or it extends that boiling point. Boiling point elevation, it keeps water from boiling off and overheating the engine. Keeps water from boiling off. So it can cool the engine. On a really hot summer day or when your engine's working really hard, you don't want that water to boil off. You want to keep it there so that you can keep that engine cool. If that engine overheats and you burn the engine, very good chance you're going to have to start over and get a new engine again as well. So that's also a really dangerous thing. So both of those things are why we use antifreeze. Okay? Next time, we are going to talk about actually creating the calculations for those temperature changes and learning how to make those calculations, okay? We didn't really talk about osmotic pressure. Just know that when we put more solute or dissolve more particles into a solution, we can raise the osmotic pressure. All right, have a great day. We'll see you. Bye.